Let's talk the p-value versus critical value approach. And with hypothesis testing, let's remember that everything ties back to that bell curve. And we're testing to see if a value is significantly different than the population mean. So if we're looking to see if something is significantly more, one thing we know about that is our null and alternate hypothesis will be, and let's just say that this is a 25 here, so our population mean being a 25, and I put mu s, and that refers to my sample, and if my sample represented the population mean, is it less than or equal to 25, and we'll draw this one, or is the alternate, which represents this tail here, greater than 25. So you've got your null and alternate hypothesis. And when we talk about the p-value approach, what we're talking about is the amount in your tails. And in this case, you have one tail. And if you use an alpha value of 0.05, which again, if you don't have one, always assume an alpha of 0.05. That means that this area here is 0.05, and then the rest of the area, this area here, is 0.95. Okay, again, everything should equal 100%. So with that, this area again is 0.05. Now if you look at z-scores or t as they go across the bell curve, the larger the value, the farther away it gets. So at, let's say, this point, if that's a z-score of 1, anything to the right of it would be greater than 1, so that could be a 2, that could be a 3, and again, let's think of this as z-scores, and so on. The larger the z-score, again, the farther away from the mean, that also means the amount in the tail for that z-score will be smaller. Okay, so I'm gonna and we've got this idea here again that there we go, and just want to make it very clear that if I'll put 25 here, and if this area is 0.05, because that's our alpha value, if we were to come up with different values, so a z-score at this point means we could look up 0.45, and actually what we would look up is 0.95, and we would find out that our z-score would be 1.645 at that point. Well, if we were to come up with a calculation for our z-score, and again, if we were to just use this as our way of calculating it, and let's say that we found out that z is actually 2, I'll do it, yeah, 2 point, oops, 5, and let's say that's our actual z-score. Well, then what is the corresponding p-value for that? Well, if that z-score is way out here at 2.55, and if I look it up on my z-score, and I'm going to look that up right from the book, and you can probably hear me rustling in the background here, and I'm pulling out my book and I'm looking, there's my positive z-scores. I go down to 2.5 over to 0.5, and it gives me that from this point over is 0.9946. Now if that's the case, then that means that this area, now that I'll put in green, is going to be 0.9946. 1 minus that, which gives you 0.0054. So that area is obviously a lot smaller the farther away from the mean that you get. So if we were to instead have z-score. And let's go ahead and draw the same thing, but let's say it's instead 1.87. Well, do you think this tail will be larger or smaller than what we got for 2.55? And the truth is, it will be, if you look it up, 1.87 is 0.9693, which means this area is 1 minus 9693, which gives us that 0.0307. So again, you can see that value is just a little bit larger than the one that you had for the 2.55. So what I'm trying to get at here is the larger the z-score, or t, z doesn't matter in this case, the smaller the tail or p-value that you'll have with it. So with this, if we can think about it, it becomes really easy. And I want you to make sure you understand this, because once we get into using Excel for everything we do, especially in Stat 2, then this becomes really important. But if you have a significance level of 0.05, then what you can say is you will reject the null if your p-value is less than 0.05. And it's that way in every single case. So if your p-value is less than 0.05, and again, like in this case, we had what, 0.0307, that value is less than 0.05, and you can see it's farther away from the mean than the 1.645. Therefore, since it is farther away, and you can look at it this way, that 1.87 would be here, and then only this portion would be that 0.0307. So p-values represent amounts in tails. The smaller the p-value, the farther away from the mean you will be. Now, taking this same approach, you can do the same thing except using critical values, and it works the same. And so you can think of it any way you want. Doing this by hand, I feel it's easier to look at critical values, but doing it with Excel, it's definitely easier with p-values. And again, I want you to make sure that you watch those videos that we've put up using Excel in our modules that show you that. But what we then do is say, okay, that's our critical value right here. So this is the critical value. And we're going to do a calculated value. And whether that's z or t, it doesn't matter. And let's do z. And so using the same formula like here. And we come up with a calculated value, whatever that ends up being. And we compare it to the 1.645. If we have a value that is greater than 1.645, we reject because we're in the tail. When you're in the tail, you reject. So you're in the tail when the critical value, again, we're talking about this side here, the critical value is less than the calculated, or it's when the sigma level is greater than the p-value. Okay, so if this number is smaller than your significance level, then means you're somewhere out here. If your calculated value is greater than your critical value, then you know you are somewhere out here. Either way, the larger the calculated value, okay, let's think about this here. The larger the calculated, that means the smaller the p-value. So if you had a calculated value of 6.8 0.89. You can imagine that the p-value for that would be something really, really small. Okay, so p-value approach refers to the amount in a tail, where the critical value refers to the actual z or t score, and then you compare the two. Okay, lastly here, and I apologize for being long-winded, let's look at a two-tail test. And if we say that the sigma significance level is 0.05, again, let's throw a 25 here. Therefore, our null and alternate is going to be equal, I'm sorry, I am drawing a little bit funky here, to 25 or not equal to 25. And in that case, you have two different tails. Well, if we're looking at z-scores, the critical value of z, when you have 0.05, that means first of all that 0.025 is in this one and 0.025 is in that one. Again, because these two numbers added up will equal 0.05. So the significance level is always the amount in all of your tails. So you either have one or two tails. And when you look at a z-score for that, that means that you would have to look up 0.9750. But regardless, we already know that it's going to be negative 1.96 or a positive 1.96. Now, the amount that I'm about ready to throw here in orange represents the null, and then the area out here represents the alternate. So if we have a calculated value that is greater than 1.96, in other words, out in this area, there we go, or less than negative 1.96, that would be in this area, then you know you should reject the null because you're in one of the tails. Again, you reject when you're in one of the tails. Okay, now let's look at, now that's the critical approach. What about the p-value approach? Well, significance level is 0.05. We reject when the p-value is less than 0.05 in every case. Okay, so the way that we do this is we still need to calculate come up with our calculated value. And so let's calculated z, and then we need to find the appropriate p-value that corresponds to that. So how do you come up with a p-value when you have two tails? Well, let's say that we end up with a calculated z equal to 1.25. Okay, so when we look up 1.25, we get 0.8944 as our area. Okay, so what does that mean? That means that if we were to put 1.25 at this point, the amount to the left of that is 0.8944. Okay, so the tail that corresponds to that, let's get rid of all of that. So the tail, this yellow area here, is going to be 1 minus 0.8944, and if I can do my math correctly here, that's 1.056. So the area that you see here in yellow is 0.1056. Now the problem is that's one tail, but this alpha value actually represents two 2 tails. And so what you then do is multiply that 1 tail, hope that's right, and you guys can check my math for me, by 2 because you have 2 tails. So your p-value is actually 0.2112. Obviously that's larger than 0.05, and as you can see, it's to the left anyways. It's in your area where you would support the null. It's also less than that 1.96, which again lets you know. So if your calculated value is less than a positive critical value of z, or greater than a negative critical value of z, or if your p-value is less than 0.05, then you know you reject. You reject when the p-value is less than 0.05, and you reject when your calculated value is greater than the 1.96 or less than the negative 1.96. So this is one of those videos I think you should watch a couple of times. You need to know both approaches. Now again, for this class, you will the critical value will probably be the most helpful, and I'm going to step you through some steps in the next 2 videos on how to do a p-value approach and then how to do a critical value approach with an actual example that'll hopefully help you out.